Okay, this is going to be a heat exchanger analysis problem involving the effectiveness NTU method. It involves a blood heat exchanger used to induce hypothermia. Some of the values to make note of: on the hot side, the blood is coming in at 37 C, leaving at 25 C. On the cold side, we have water coming in at nearly or at 0 C, so it would have to be some sort of saline solution to ensure that. And then exiting at 15 C. The physical properties of blood are shown here and here, both the density and the specific heat. The volumetric flow rate of the blood is also shown. The flow rate, however, of the coolant is not known. The water is not known. And the overall heat transfer coefficient is shown here at 750 watts per meter squared K. And the goal of this particular problem is to calculate the heat transfer, the flow rate of the coolant, and the area. So let's try to work through it. The first idea I think that's important to do is to try to visualize what's going on. So let's do that. You have a bloodstream that is being cooled. That's an inlet and an outlet. And the problem assumes, although not carefully stated, that the flow in this particular problem is cross flow. So we usually consider that counterflow. That's how it's depicted here. And it's also assumed, so I should make these assumptions here. Cross flow to unmixed. That will be important down the road as we go and pick the correct effectiveness NTU equation. So, what we have, it's not really fully labeled yet, so let's wait 1 second. Let's make sure we get this. So this is T hot in, T hot out. This is T coolant in, T coolant out. This is obviously a temperature scale, and this is a length scale. We usually call it X if we call it anything. But it's the flow along this heat exchanger. And it's shown over here, so it turns out that the coolant is coming in here and out there, and the bloodstream comes in here and out there. That's a view of the pattern here. A cutaway is shown there. So let's jump on this one. First goal is to calculate the Q, and we know, so this is the analysis. Q equals what? Well, it certainly equals the heat, or I should say heat transfer to the hot fluid, as well as heat transfer to the cold fluid. This assumes no heat loss. So how do we calculate QH? It would be the mass flow rate times the specific heat times the change in temperature on the hot side. These indices can add clarity, the subscript H's. Now what we need to do is calculate M dot, which is rho V dot. These both are given to us. We just have to make sure we get them in the right units. This is given to us, and so is that. So let's march forward. The mass flow rate would be equal to flow v dot, which is 1050 kilograms meter cubed times 5 liters per minute times 1 minute 60 seconds. We're seeking kilograms per second. We're going to then convert the liters. 1 liter equals 0.001 meters cubed. And then we're going to check the units, making sure the minutes cancel, the liters cancel, the meters cubed cancel, and you're left with kilograms per second. This value is 0.875. I should make a correction there. It's 0.0875 kilograms per second. Now we can calculate Q. QH as 0.0875 kilograms per second times the 3740 joules per kilogram Kelvin times the temperature change, so it's 37 to 25. Remembering that the delta in Kelvin is the same as the delta in Celsius. So what can we say now? This is equal to almost 4 kilowatts. And you can see how the units cancel. This is a Kelvin. So the Kelvin is canceled, kilograms canceled, and now we have joule per second, which is watts. Alright, so we're on our way. We've gotten our first solution, and that's the amount of heat that is transferred away from the blood and to the coolant. If there was any heat losses around the outside of this heat exchanger, we couldn't claim this right here. So now let's go to calculate the mass flow rate and the volumetric flow rate of the coolant, and that's a simple matter. Let's just make sure we label this as solution for A. Now let's go for B, and we can say the Q coolant is the mass flow rate of the coolant times the C sub P of the coolant times the delta T of the coolant. And so we can say that the mass flow rate of the coolant equals Q sub C, Cp sub C, and delta T sub C. Putting in the numbers, 3927 watts divided by 4198 joules per kilogram. And that's a pretty typical value for water. Times the 15 to 0 temperature change. So you've got Kelvin. Again, the delta in Kelvin is the same as the delta in Celsius. Those cancel. This goes to a joule per second. So the joules cancel. The kilogram goes on top. The units look good. The value of this is 0.0624 kilograms per second. What is that in terms of volume? Well, we know that mass flow rate for the coolant equals rho of the coolant, volumetric flow rate of the coolant. Therefore, volumetric of the coolant equals the mass flow rate of the coolant divided by the density of the coolant. Now that we put in those values for mass flow rate, so it's 0.0624 kilograms per second. And how does that compare to the mass flow rate of the line? Okay, so it's slightly less. No, I shouldn't say slightly, but let's say 20-30% less. Divided by the density. And again, we'll use a common value for water. If you check the water properties, this value doesn't change much with temperature, at least around this range. And now you've got a meters cubed per second. If you don't want to go to meters cubed per second, well, let's do it. .0624, enter, 1,000 divided by, obviously it was an easy calculation, 624 p -5, and that's going to be meters cubed per second. And now to convert that, we'll into the proper units, liters per minute, we'll go 6.24 p -5 meters cubed per second times, let's see, 1 liter equals 0.001 meters cubed, and then there are 60 seconds per minute. And the value of that becomes 3.74 liters per minute. Alright, so we're done B. Now let's go to the last section. This last section is going to require us to use the epsilon or effectiveness NTU method. So in order to use that method, we need to calculate some initial values, most notably the heat capacity rates. So let's do that. There's a high temperature heat capacity rate, m dot h c sub p h, and that value is 327 watts per K, c sub c. So the heat capacity rate for the coolant equals, see, 262 watt per K. Now if we reflect on what the epsilon NTU method will require us to do, we know that we're going to have to calculate what they call a heat capacity rate reduced value, so this C sub R value. And that's basically C min divided by C max. Let's do that. 262, enter, 327 divided by, so it's 0.801 value. We also should calculate Q max. These are just kickoff calculations that you should right away attempt when going after the epsilon NTU method. So Q max equals the C min times the delta T max. So that value is 262 watt per K. The delta T max, again, is the T hot in plus the coolant in. So in this particular case, it would be 37 minus 0. And that's in Kelvin. At least that's the change would be equivalent in. So you've got a maximum wattage of almost 10,000 watts. So it's a bit short in terms of effectiveness. We can calculate that. Q actual divided by Q max. And that's just going to be the 3927 divided by the 9694, they're both watts, and you get a value of 0.405. So that's the effectiveness of it. It's 40% of the way to a optimal or maximum heat transfer value. So how do you find the area now? Well, because you have the effectiveness and you have the C sub r, if you recall, the effectiveness NTU method allows you to relate these into a function. So, broadly stated, epsilon can be equal to a function of NTU and C sub r. All of these functions depend on the type of heat exchanger. So, if you go to this particular table, you can find, actually it's the table above, I believe, you can find a relationship that involves unmixed fluids in a cross-flow situation. So this is the equation that you want to grab. It's equation 11.32. It's kind of complicated, but that's the one that you'll choose for this particular problem. So let's write it out. Epsilon equals 1 minus the exponent, first bracket, second bracket, 1 over C sub r times NTU raised to the 0.22, third bracket, another exponent, another bracket, negative CR NTU, this time it's raised to a 0.78, close that bracket, minus the 1, curly bracket, and then the final bracket. What you would do now is to plug in the values for C sub r, wherever they're located, effectiveness, and you would solve for the only variable, which is NTU. You can do that on your calculator in ease. The value turns out to be 0.691, and because we know that that equals the overall heat transfer coefficient, which sometimes has a bar, the area and the C min, we know C min, we know U, that was given in the problem right at the beginning. The last remaining unknown is the area. So now we plug in shug, and you've got area equals 0.691 times the 262 watt per K divided by 750 watt meters squared K. Does it work? Let's look at the units. Watts cancel. K cancels. So meters squared come out. The final value for this particular heat exchanger, 0.241 meters squared. So let's review this problem a little bit, because that is the final answer. Let's go up to the top and review a little bit. First, as you attack a problem like this, try to visualize it. Try to visualize, in particular, the temperature versus flow behavior here, right here. This is where you want to focus. I should say temperature versus location in the heat exchanger behavior. This temperature, high temperature, enters and leaves. This cold temperature enters and leaves. Physical visual can also help. make sure that you clearly write down what's given, recognizing that temperatures, flow rates, heat transfer coefficients, and properties are the typical values that you're looking at in heat exchanger analysis. For the most part, you will not talk about pressure drop in a standard heat exchanger problem, and that's really a mistake. We should. We also have to be clear about what we're trying to find, and we do here with Q, V dot C, and A. You should also be clear about the assumptions. As you work through the problem, remember the classic assumption in the heat exchangers is that there's no heat loss. All the heat is exchanged between the cold and warm fluids, or cold and hot fluids. The first law never goes away, and it should be really the starting point for almost every single heat exchanger problem you tackle. In this case, we attacked QH, and we were solving for the QH. So since we had the V dot sub H, and we had the properties for rho, we were in good shape. A is a straightforward calculation. This next calculation for QC, just make sure this is clear, was also straightforward. We were just basically solving for the one unknown, which was this one, M dot C. We knew the C sub C for water, that's straightforward. We knew the temperature change of water. We also knew that QC equals QH. Finally, to finish off the epsilon NTU method, we chugged through the basic calculations of the C sub H, the C sub C, the CR, and the Q max. Once we had those four preliminary calculations, we could calculate the epsilon, identify the correct epsilon function, which again I should really emphasize is dependent upon that type of heat exchanger, and pull the function in, solve for the one unknown variable, which is NTU in this case, then equate that NTU to its classic definition of UA divided by C sub min, and solve for the last remaining variable. I hope the problem was interesting, and I hope this explanation is worthwhile. Thank you.